Hello students, welcome to my YouTube channel Easy Mathematics. From this lecture onwards, we are going to start the advanced graph theory. And the first topic of this advanced graph theory is tree. Tree is a special kind of graph, which is the most powerful graph of the advanced data structure, and it often pops up in even more advanced subjects such as artificial intelligence, compiler designing, and circuit theory. The tree can be manipulated for hierarchical data, make informations easy to search, manipulate short lists of data as a workflow of compositing digital images for visual effects and router algorithms. In fact, there are vast application area of this tree. So what is tree? A tree is a simple connected graph. A tree is a simple connected graph without any circuit. So, for example, let us consider this one as a graph. Only one vertex is there. So, no circuit is there. It is a simple graph and it is definitely connected. If we think of a graph with two vertices only and it is connected by one edge. So, no parallel edge, no self loop is there. So, it is a simple graph and it is connected also, and it have definitely no circuit. Circuit means in between two vertices there should be a path, in fact two paths if the circuit is formed, but here only one path is there from the one vertex to another vertex. So this one also we can say as the tree. For another example, we can think of the vertex with graph with three vertices. Here also this one is a simple connected graph without any circuit, so it is also a tree. Again this one, here the total 5 vertices are given and no circuits are there, so it is also a tree. In fact, this one is again a graph without any circuit and it is a tree. There are few basic terminologies which we used in case of the tree. So tree in general, in our environment we find out the trees. So these trees we have the root, the branches, the leaves and all. Here in the graph theory also we can find out the similarity with that tree even. But the basic difference is our graph theoretic tree is just the reverse of the natural tree. That means root lies in the top and the leaves lies in the bottom of the tree. So at first we come to know about few terminologies. So first one is the root. So what is root? The topmost node in a graph is a tree. The topmost node in a tree is called the root. So here this one we can say as the root, this one we can say as the root, here this one we can say as the root, and here this one we can say as the root. Next it is the pendant node. So a node that has a child node is called the parent node. So now look, here any node which have the child means if from one node any edge is going out, then these are termed as the child. So this one is the parent node for these two edges. Similarly, this one is the parent node for these two edges. Again, this one is the parent node for these two edges, and likewise. Next is the siblings. Siblings are what? Nodes with the same parents. That means we can say these two nodes are the siblings because both of these two nodes have the same parent. Again, these two we can say as the sibling because it's both for them have the parent, this one. Next it is the internal nodes. Internal nodes are that nodes which lies inside the graph. So the node with at least one child is called the internal node. That means if any node is given and it have any child node, then we can say the node is the internal node. In fact, except the root and except the lower nodes, whatever the nodes lies in the graph, these are called the internal nodes. So for this graph, this one, this one, this one, then this one and this one, these are the internal nodes. Next it is the leaves. So leaves are what? That is the nodes with no children. So these are the end nodes. So here this one we can say leaf, this one, this all are the leaves. In fact, we can say the vertex with degree 1 is the leaves. So look, any vertex in a tree with degree 1 are termed as the leaf. These are also called the pendant node also. Next, it is the height of a node. So what do you mean by the height of a node? That is the length of the longest downward path between the node and the leaf. In this graph, we can say the highest node is this one, because 1, 2, 3, that is the longest path in between these two nodes. Next, it is the label. Label is one of the most important thing in the tree structure of graph theory. So what do you mean by the label? So label is the number of edges between the node and the root. So here in the graph we can say the first node, this one is at the label 0. Then its second step, these nodes are at the label 1. Here the label 0, these are in label 1, these are in label 2. Now here this one is label 0, this one label 1, this 4 are in label 2, then this one in label 4, and these two are in label 5. And one more thing, that is called the forest. So a set of n greater than equals to 1 disjoint trees are called the forest. So if we consider all those graphs together, then this together may create the forest. So these are the few terminologies regarding the tree. Next, it is some important theorems on the tree. So the first theorem is, in a graph G, there is one and only one path between every pair of vertices. Then G is a tree. So how to prove this one? What is the theorem? In a graph G, there is one and only one path between every pair of vertices. Then G is a tree. So how to prove this one? If there is a path between every pair of vertices, then G is connected. That is very obvious. Now we have to prove that G has no circuit. If we can prove that G has no circuit, then we can prove that in between any two vertices there are not more than one path. If we can prove that in between any two vertices there is exactly one path, then we have done. So a circuit in a graph implies that there is at least one pair of vertices, say U and V, such that there are two distinct paths between U and V. Since G has one and only one path between every pair of vertices, therefore G can have no cycles. And when G have no cycles, then we can say the graph is a tree, and hence the theorem. Next theorem is, a tree with n number of vertices has n minus 1 number of edges. This one is the most important theorem in our tree. So what is the theorem? In a tree with n number of vertices has n minus 1 number of edges. So how to prove this one? Let a graph is given which is T. So this one is suppose the given graph. Now the theorem can be proved by method of mathematical induction depending upon n, the number of vertices in T. Let T have containing n number of vertices, and this one is a tree. So E is one of the edge of this tree. So this edge connects the vertex V2 and V5. Now if we just remove this edge from this tree, then what happens? This tree becomes disconnected. If we remove this one, then this tree becomes disconnected. So now we know that every disconnected graph consists of two or more connected graphs called the components. So if we remove this edge, then what happens? This one is one part of the graph and this one is the another part of the graph. So the graph becomes the two parts, and we can say each of these two are the two components of the graph. So after removal of E, we will find out the two components of the graph. So now the graph T minus E, that means this graph after removal of E, the newly graph is T minus E, which is this one. So this one has exactly two components. Say the first component is T1 and the second component is T2. So pictorially we can say this one is our T1 and this one is T2. Now let T1 contains n1 number of vertices and T2 contains n2 number of vertices. Then the total number of vertex should be n1 plus n2. Now if T1 contains a circuit, then T would have a circuit. It is very obvious. If T1 contains a circuit, then T definitely contains a circuit, which is not possible. So T1 is a tree. Similarly, T2 is also a tree. So by our hypothesis that T1 has n1 minus 1 and T2 has n2 minus 1 number of edges. Thus, T minus E consists of n1 minus 1 plus n2 minus 1 is equals to n1 plus n2 minus 2, that is n minus 2 number of edges totally. So T minus E, that graph contains the total number of edge, which is n minus 2. Now hence the graph T has total n minus 1 edge because one edge we have removed from T to get the T minus E graph. So n minus 2 is the total number of edge for T minus E. With that, if we add this one removed edge, then we will find out the total number of edge is n minus 1, and hence the theorem. Here you should note that the converse of this theorem is also true. That is, the connected graph with n number of vertices and n minus 1 number of edges is a tree always. So one more theorem for the tree structure is that a graph is a tree if and only if it is minimally connected. So minimally connected, what does it mean, the minimally connected? A connected graph is said to be minimally connected if removal of any one edge from it disconnects the graph. That means if we remove one edge and at least any one edge from the given graph, and after removal of that edge, the graph becomes the disconnected, then we can say the given graph is a minimally connected graph. And for a minimally connected graph, that is always has to be a tree. Just because, just look at this one is the example of a tree. Among these edges, if you remove any one of the edge, then we will find out the graph becomes disconnected. Here we remove this one, so it becomes in two parts. Instead of this one, if we remove this one, then this one is the one part and this vertex remains in the second part. So any one edge you may remove from this graph, you will find out that the graph becomes disconnected. So a minimally connected graph is also termed as a tree. Now one problem for the tree, let us do here. So what is the problem? The problem is a tree has two vertices of degree 2, one vertex of degree 3 and 3 vertex of degree 4. Now how many vertices of degree 1 does it have? So how to solve this one? So what is our requirement? Our requirement is how many vertices of degree 1 does the tree have? So initially let x be the number of vertices with degree 1. So now the total number of vertices in the given tree is n, which is 2 here because it is given that 2 vertices of degree 2, 1 vertex of degree 3 and 3 vertex of degree 4 and x vertex of degree 1. So this is the total number of vertices in the given graph, that is 6 plus x. So now, hence the number of edges should be, we know, n minus 1. Hence the total number of edges is 6 plus x minus of 1, that is 5 plus x. Now the total degree of the given graph. So in the given graph, it is in the problem given that 2 vertices with degree 2, 1 vertex with degree 3 and 3 vertex with degree 4, and according to our hypothesis, x number of vertices with degree 1. So if we do this calculation, then it will leads us the 19 plus x, that is the total degree count for the given graph T. Now by the handshaking theorem, the total number of edges in a graph, we know that is the total degree divided by 2. So now if we equate these two equations, that is equation number 1 and this is equation number 2, both are same. So if we equating these two equations, then we will find out 5 plus x is equals to 19 plus x by 2. If we simplify, then we will find out x is equals to 9. Here, if this one is the graph, so here we can say that total number of 9 vertices are there with degree 1. So for real example, if we consider this one as a tree, then here the vertices with degree 1 is 1, 2, 3, 4, 5, 6, 7, 8 and 9. In fact, you may draw any tree and accordingly you just calculate, you will find out this number will be according to this theorem.